Hi everyone, my name is Marcus, um, and my talk today is about my journey in learning PCB design and how I apply it along with the rest of my team on amateur rocketry. So you can see some of our early creations over here. So this is our very first attempt at avionics, which means like the rocketry flight computer electronics. So this is an Arduino Pro Mini, which in our absolute expertise, we soldered the headers on backwards. So the reset pin faces the breadboard and we have the preset and Allen key. The LoRa on this thing, so this was a LoRa test board effectively, and with that crappy coil antenna, we got like 800 meter range, which was not bad, you know. The second picture is the very first version of our flight hardware. So we call it Avionics B V1, this being Avionics A. So that board was gigantic and crude, but it was our first real attempt at PCB design. And the third picture is the flight computer inside of kind of like the structure that holds it inside of the airframe. And finally, the last picture is a sneak peek of the second version of Avionics B, which is significantly improved. So when we started this out, you know, I had never touched electronics before. I've always been a mechanical guy. So doing like gearboxes, robot arms, competitive robotics, this sort of thing. I barely knew what a capacitor was. Okay, so I'm from the rocketry organization Spacebar. We are a Singapore University of Technology and Design organization, and we fly rockets. So this is the first rocket that we ever flew. And our official mission is to make aerospace accessible, but of course, we have other things going on as well. The Singapore University of Technology and Design, all the way out in Upper Changi. And we started in May this year, and we've since built 6 rockets and launched 3 of them. So this is our team now, and 2 of them are actually here up there. Yeah, so we've grown quite a lot over the months, and we're still doing more. So Zoom is still up here. Oh, so we fly in Malaysia and Australia. You can't do anything here. Yeah, whole countries are no-fly zone except city center, which has other problems, you know. So, okay, so our key objectives: we build rockets, we engineer high-altitude vehicles, and we attempt to innovate within them. And we have research and development in real-world scenarios. We give students a chance to exercise their passion in aerospace, which is a rare thing in Singapore. And we provide opportunities to learn and lead, of course. So the basic principle that every flight is a first things. Long-term technical to reach the Kármán line, the boundary of space at 100 kilometers up. So in the next 2 years, you know, we've done Figurehead 1 and Flagship 1 already. So the next 2 rockets that we're working on, the first one is dual redundant avionics. So not just 1 computer, but 2. So other one's still there. And also that rocket is going to be doing active roll control, which means that the rocket can, as it goes up, it can change the way that it's facing that. And the other rocket that we're going to be flying in February is a supersonic test. After that, we're going to go on to full 3 degrees steering. And then we're going to go on to 2-stage rockets. And then we're going to put everything in 1 rocket and fly that. And from there, we're going to do bigger and bigger rockets, larger and larger payloads, higher and higher, until we hit space. That's basically the plan. But anyway, I'm mainly here to talk about our avionics today. So our design philosophy is a bit weird because we have to guarantee that our system is going to work, and we have a very rapid flight rate, so we can't do too many iterations. So as novices who are like basically just starting out in PCB design, we have to guarantee that our avionics is going to work, you know, and you know, somehow we have to figure out how to make something reliable, even though we have no idea what we're really doing, right? So we design backup plans. So we try and make the system as robust as possible to begin with. You know, to the best of our knowledge, we say, okay, look, maybe this thing is gonna brown out or something, we do something about that. You know, these sorts of basic things. But not just that, wherever possible, we introduce redundant systems, and not just redundancy in the form of like identical copies, but dissimilar redundancy. And the idea of that is, let's say one component has some failure mode. If we copy that feature over to multiple other computers, and those computers implement that feature in a different way, different components, different software, and hopefully the failure mode does not also apply to the other computer. Also, the flight computers, as much as possible, are reconfigurable. So if something goes wrong, no problem, you know, reconfigure and readjust. For example, we work with Australian explosive licensed professionals in Australia when we fly there, and the igniters that are used are effectively nichrome wire with a bunch of pyrogen wrapped around them. So if this thing has an unpredictable electrical characteristic, it could short, it could like draw a crazy amount of current. Nobody knows, you know. So a lot of the complexity around the avionics is getting things to ignite properly without knowing exactly how the igniter behaves. So basic avionics design requirements, there are actually quite a lot that goes into a rocket. I'll go through it real slow, don't worry. So the first thing that we need to do is trigger flight events. So a rocket has to do things during its flight. It has to go up and then come down, right? So going up, it has to ignite the motor. And coming back down, it has to deploy parachutes. And the parachutes ensure a safe landing velocity. So you can have up to 2 parachutes for each stage of a rocket. And we call this a main and drogue setup. So the drogue setup is a real small parachute, and basically it slows us down from free fall, but we're still falling pretty fast. And we fall fast so that we don't drift by the wind, so that the rocket doesn't go like kilometers away and we can't find it. So we fall real fast first, then we deploy the main parachute later. The main parachute is way bigger, and it arrests our velocity to a much more manageable speed so that the rocket doesn't shatter on impact. So these rockets deploy the parachutes either through pyrotechnic ignition or pneumatic pressurization. And we lean more towards pneumatic pressurization just because we can actually test that in Singapore. Pyrotechnics, not so much, you know, in fact, not at all. Motor ignition as well. So that's something that has to happen in flight, especially for a 2-stage rocket. You know, for 1-stage rockets, you can really just light it using a ground control station. But in 2-stage rockets, you have to light the second motor in the air. And there's a whole bunch of safety lockouts that have to go into that. Finally, camera control. Our rockets have onboard cameras, and I'll show you some of that footage later. And the cameras, we need to be sure that they're recording, because I don't want to fly the rocket a second time, you know? Yeah. So additionally, we have motion sensing and flight path tracking. Every single flight, we aim to learn something new. So we need to get as much data out of that flight as possible, and we need to be very sure that we're not going to lose the data. So that's what the rest of the avionics job is. So we got an IMU on board, inertial measurement unit. It's just a little MEM sensor, quite common. It's got an accelerometer and a gyroscope on board. And what that does is it gives us linear and angular acceleration. We can integrate this down to get position and velocity, but this is an inexact way of doing things because integration is always by adding up time steps, and time steps are not accurate. So we say that the data drifts, which means that over time inaccuracies build up. So the rest of the sensors are a little bit more absolute. They don't drift, but they have other problems. So we have a magnetometer, and what the magnetometer does is it senses the Earth's magnetic field. And using this, we can get a decently accurate hitting that doesn't really drift, but it's still affected by like big motors spinning in the rocket or such things. So that's a problem. We have the barometer, which is a pressure sensor. We use this to detect atmospheric pressure changes. It's a good estimate of how high we are. Unfortunately, the barometer also has problems. So if we transition from subsonic to supersonic, oblique shock waves around the rocket cause weird pressure waves around it, which makes the barometer untrustworthy. So finally, we have a GPS. The GPS is, I mean, just a regular GPS, not gonna lie. I'll show you later. But we aim for a multi-constellation GPS because the more satellites we have in range, the better we can corroborate our data, and hopefully we'll get slightly better CEP, which means accuracy. And also we've got telemetry right next to the GPS. So we really look for antennas with good out-of-band interference rejection, which just means, you know, any radio frequency stuff happening from the telemetry or anything else on the rocket, the GPS is going to ignore it pretty well. It's just going to focus on GPS frequencies range. Finally, we have data logging and telemetry. So data logging and telemetry is where a significant amount of the redundancy is. So it's not just about whether we implemented the data logging incorrectly. It's also about whether we even get the rocket back in the first place. So We have an SD card as primary data logger because they're convenient and they have big file size. But SD cards have the problem where if the rocket undergoes high dynamic load, we will have a significant amount of vibration. And every now and then, the SD card manages to wiggle out of the socket. We hot glue the SD card in place, but still, we are worried, you know? So in addition to the SD card, we also have an onboard NOR flash memory. So NOR flash is a non-volatile form of memory. Usually we communicate with like quad SPI, and non-volatile is important because if the rocket fails to deploy its parachute, it shatters on the ground and the PCB has either lost its battery or shattered in half completely. Hopefully we can just desolder the memory, put it on another board and retrieve the data that way. It's a bit silly, but this is what people do and it does kind of work. Yeah. Finally, we have the telemetry. We just use LoRa. We're looking into, you know, Zigbee and some SARS stuff. Was it you who had the SARS? Yeah. So we got a couple SARS members in our team, and we're working on getting more licenses, and hopefully we'll be doing like some larger radio stuff. But so far, we're basically just doing hobby radio, hobby LoRa, and the LoRa kind of acts as like a tertiary backup telemetry. So if we lost the rocket completely, you know, hopefully the data was transmitted intact down from the rocket. So this is our Avionics BV2. It's our flagship board, and we've packed as many features on board as possible in the hope that we future-proof for future flights, because custom PCBs are not that cheap, and I would like to not have to do so many iterations. So we packed as many things as possible onto one board. Yeah. So Avionics B packed a whole bunch of extra features on top of the essential functionality. So down here, I've got a picture of the KiCad routing. So this is just KiCad is an open source PCB design software. It's quite nice. Yeah, anyway, so we've got battery sensors on board, which the original flight computer didn't have. So we've got current sensing on board and voltage sensing, and this allows us to check for over discharge and battery surges. However, minor oversight, we can sense the battery doing things, but we absolutely can't do anything about it. So this is something that future boards might fix. Yeah. Best we can do is, oh, the battery is low. Let me just change the battery before we fly. You know, that's about the best we can do right now. Then the multifunctional pyro channels. So the pyro channels have got a whole bunch of sensors on board. The pyro channels are what we use to ignite pyrotechnic ignition. Like I said, pyrotechnic ignition is a bit of a question mark when it comes to the electrical characteristics of the igniter, because it really is just a nichrome wire wrapped in pyrogen, and it just heats up and it ignites and hopefully doesn't short or anything. You know, so we've got current sensing on board to check how much current the igniters draw. This is mainly for ground testing right before we fly, and then we can set the current limit accordingly. So we've got dynamic current limiting chips on board as well. So if the current surges above, like for example, 4 amps, then we can configure the thing such that it's going to hold at 4 amps and never try and go higher. It will electronically limit. It's not a fuse that I have to replace. We have continuity sensing as well. This allows us to verify that the igniter is connected properly before we fly. It would be unfortunate if we forgot to plug it in, you know, so it'll set off an alarm if it's not plugged in before we fly. Voltage measurement as well. This is purely for us to see, because why not? It was not an extra feature that we had to add. The chip came with it. And finally, we have hardware reconfigurable output voltage and I2C addressers. So the output voltage is configurable via headers. So by default, we run it off 5 volts, the igniters, but if need be, we can run it off raw battery voltage, you know, just in case the igniter doesn't seem to be firing very consistently. We'll just up the voltage, no problem. And the I2C addressers for the pyro channels, basically they're all hooked up to one I/O expander because we put way too many features on the board. So if it so happens that we manage to blow up one of the pyro channels because an igniter drew way too much current, no problem. You know, I don't even need to take out my computer and change the code. I'll just change the headers on board and we'll remap the pyro channels that way. Finally, aileron control. So some of the later rockets that we're doing are going to have active steering on board, which has a whole host of safety lockouts required, which is another topic entirely. But effectively, we use servos to control ailerons, just like hobby drones or planes that use ailerons. It's the same idea, you know. So we've got servo ports for active steering, and again, we have reconfigurable output voltages, but this is more for ease of design in future so that we're not limited to like a certain voltage when choosing servos. And we have a fast main processor for heavy extended Kalman filter computation, because all of the motion sensors that we're doing, the IMU is the main guy, but all of the other sensors are absolute. So we sensor fusion everything together with an extended Kalman filter. And this way we're able to get a little bit of a smoother sensor curve. We haven't quite gotten this dialed in, but it's still better than nothing, So anyway, so here's another picture of the avionics. Oversight, I forgot to bring it. Sorry. But yeah, so we've got a multi-constellation GPS on board. It's a U-Blocks module, which we implemented ourselves. So it's done directly on the PCB, and we did a bunch of RF design. Very amateur RF design. Basically, we just put as many stitching vias as we could possibly fit on the ground planes, and like it better be enough, So we can hit all of the major GPS constellations at about 10 hertz with about 1.5 meters CEP, which means that the GPS is pretty sure that we're within 1.5 meters of where it says it is. We have motion sensors on board, so barometer and 9-axis IMU. 9-axis means that the IMU includes the magnetometer within it. Primary and backup data logger, as previously mentioned. So the processor is an ARM Cortex M7, and that's just a Teensy 4.1, actually. Teensy 4.1 is effectively an Arduino, as far as any programmer is concerned. You just kind of hack the Arduino IDE a little bit with Teensy Arduino, which is PJRC's software. And now you can program an ARM Cortex M7 as if it's an Arduino. And this is great, because it's not like the Teensy, for what it is, the Teensy is affordable because it's got a great amount of features, a huge amount of GPIO. Yeah, finally, we have like, the LoRa, the pyro, the battery sensors, and the servo ports. Not much to say there because I said it already. This is our backup flight computer and our latest and greatest. So the team has expanded significantly since we started designing Avionics B. So Avionics C had a lot more people working on it and a lot more people who were able to design review it. So there were less problems with the board. Avionics B had a couple of problems that escaped design review during manufacturing. For example, I used a N MOSFET as a high side switch. So it doesn't fire, it doesn't want to switch that part, which means that I cannot enable and disable continuity sensing. So we have to short across it or change to a PMOS. Small thing, Yeah, minor oversight. Yeah. So Avionics C was designed a lot better. It's a lot smaller as well. It does most of the things that Avionics B does, except active control. So it doesn't have aileron control because we don't want two computers fighting the ailerons. So Avionics C doesn't have as many active features. So the pyro channels are a bit dumber, but they do have higher current capacity. So fine. We've got a backup telemetry and GPS this time. So effectively, why we did this is whenever we design a new board, we're not totally sure that we got the GPS implementation right. So no problem. We break out extra UARTs, and if we messed it up, we'll just UART out a peripheral GPS, for example. We had the same thing on the version 1 of Avionics B as well. Then we have a more robust system for Avionics B. So this time the SD card slot is a mechanically locking one. So it's got a little lever that kind of crimps the thing in place like a CPU. It's much better. And we've got a dedicated high G IMU for extreme acceleration spikes. So Avionics B was able to do up to 32 Gs of acceleration, but we're already kind of pushing the limit of that. So the biggest rocket we've done so far pulled 20 Gs of acceleration and could have easily gone more. So this one's rated to 80 Gs, no problem. Finally, a backup battery. So because our pyro channels are dumber this time, we have a backup battery system. So we've got 2 XT30 connectors on the board instead of 1. And this allows us to connect an extra battery in series if required. So again, this is just another thing about reconfigurability. It would be nice if we could get to Australia and the igniters were really working, just connect an extra battery if it's not working. Yeah. So down here's a KiCad of the board. It's a bit more dense. It's hard to see anything, but I can show KiCad later if anyone's interested. And on the other side, that's an X-ray that the manufacturer sent to us. So the board is actually in manufacturing right now. It should arrive in like 5 days. Yeah, so I don't have a physical picture of it. Yeah, so this board runs on an ESP32 instead of a Teensy. We realized that 600 megahertz was too much compute power for an EKF, and we could get away with less. So this does like 240 megahertz, we'll be fine. and this time we have Wi-Fi and Bluetooth on board, just in case we want to make a ground station that allows us to configure the rocket over Wi-Fi or Bluetooth. It's purely an option. We don't really need it, but it's nice to have and might as well. So the pyro channels are dumber than Avionics B, but they are higher current capacity and they have the backup battery. So they should be just as reliable and much simpler. Motion sensors. So the barometer is more accurate, and the IMU, we have a dual IMU on board. So we have a 16G precision IMU, which is useful for most of the flight, but we've also got an 80G high G IMU, which is less accurate, but is good for acceleration spikes, such as, at the initial motor burning. And we have a magnetometer on board, which is separate from the IMU this time, because we couldn't find like a nice IMU, which is also has magnetometer on board. Apparently all the modern ones don't have magnetometer on board anymore. I'm not sure why. The LoRa is also much improved. So we chose a LoRa this time that has more like 10-kilometer range. Avionics B can only do up to 3 kilometers, and we simply did not know that there were better LoRas. Yeah, would have been nice if we did more research. Multi-constellation GPS. We have a newer generation of U-Blox GPS on board right now. So the previous GPS on Avionics B was 9th generation. This one is 10th generation and should be a lot better. We also have the robust SD card on board, and again, primary and backup data logger, just like the other Avionics. So this was our very first flight, running the very first version of our flight computer. I've never seen such noisy data in my life. This is the onboard footage from that same rocket. Might be upside down. Parachute deployment. And a safe touchdown at about 6 meters per second. Yeah, the whole rocket's carbon fiber, it can handle it. This is our latest rocket. It went up 1 kilometer and pulled almost 20 Gs of acceleration. We placed the camera too close to the motor. So what we're working on now is Figurehead 2 and SideQuest 1. These are our next two rockets. Figurehead 2 is a testbed rocket for supersonic single-stage flight, and it's also going to have a double parachute on board, so a drogue and main system. SideQuest 1 is our testbed rocket for active roll control and also dual redundant avionics. So both Avionics B and C will fly on SideQuest 1. And tentatively, we've scheduled our launch for February next year. If you're interested to learn more, interested to chat with us, we're always happy to chat, we're a bunch of nerds too. And you can contact us, you can reach out to me through Sam, or I'll be in the Telegram as well, along with the rest of the people who from my team who came today. And yeah, any questions? Okay, so we are using drone camera. So we're using RunCam Split 4s. And the RunCam Split 4 is great because it's a tiny sensor on a long cable, and then it's got a little PCB. So I can put the sensor wherever I want, and then just put the PCB like somewhere convenient later. So this means that the camera handles all of its own processing and recording on board and saves to its own SD card. All we actually do is provide power to it via one of the pyro channels. The pyro channel has current sensing capability, and if the camera is recording, then it will draw more than like 600 milliamps of current, and we know it's recording. If it's idle, then it's not recording, and we're not flying until we fix it. Yeah, so we handle all of the video processing on board of the camera itself. However, future flights are going to have like 3 or 5 cameras per rocket. So minimally one looking down, one looking up, and one looking out to the horizon. And it's going to be annoying to configure 3 cameras. So we're looking into getting a VTX just like a drone, and like just piping everything back down to the ground as well.
I have a very specific question. So you said that but in the plans, you have multi-stage rockets. So my really stupid question is, once you have multi-stage rockets working, what is even missing to go arbitrarily high? Like you can just put more fuel, make a larger rocket, make more stages.
Yeah, that's absolutely right. So having two-stage rocket instead of one-stage rocket allows you to go about 40% higher with the same amount of propellant. I mean, that there's a lot of factors to there, but that's kind of like the rough ballpark number. 3 stages is about the max that people do before it starts getting like complicated, you know. So basically when things get weirdly difficult, the larger the vehicles get. So, you know, aerostructures and avionics, everything suddenly is reciting way higher Gs, like the in the end, it becomes about reliability. You know, how much can we tune our manufacturing and design process such that we can guarantee that the rockets are more and more reliable? Because these rockets are already pretty reliable. You know, there's not a lot that can go wrong. But the bigger the rockets get, the kind of like more responsible we have to be, and like the more things that we're gonna know, and hence it enables us to be more reliable. You know, so the point of all these test flights is to prove out new technology and say, I know for sure that if this is gonna fail, it's gonna fail in a safe way. And we start from the small scale first. But you're absolutely right to say that, like, from a pure, very new technology development point of view, there's not much difference between Flagship 3, which is dual stage with active control, and Flagship 3, but 10 times bigger. There's not that much like real technology difference. It's more about process control at that point. Yes. The what lockout? Okay, so he's referring to the COCOM lockout for GPS, which basically says that it's not going to operate up above like 50 km or above like 500 meters per second. So effectively, the way that we deal with the COCOM lockout is we say that we don't need GPS for that part of the flight. Okay, so the reason why we're able to make this compromise is that the GPS is useful as an absolute measurement of position, which has a very large band of error, right? But the thing is that as far as the rocket is concerned, all it has to do is correct its path when going up. So really, the most important job of the GPS is to give us a very accurate and very reliable position that the rocket landed, so that we can retrieve the rocket. Because in flight, the IMU only needs to integrate once to get velocity. It does not need to integrate twice to get position. The rocket doesn't care where it is as long as it's going straight up and it's going up safely. So the GPS ends up not being integral for controlled flight. It's more integral for, let's say we did something wrong in the code and the flight data is all off. At least the GPS is still there and we can find the rocket later. Because we fly a lot in farmland, you know, we fly a lot in big empty plains, or a lot of rocketry sites are in deserts with like mountains, you know, so it would be nice that we can find the rocket later. If it lands 10 kilometers away, there's no way to find it without GPS and without telemetry to send the GPS data back to us. But that GPS, that last known position, that COCOM limit doesn't apply there. So we're fine.
Pyrotechnics. You normally can't fly in Singapore. You can't test your motors and parachute cover charges.
Yeah, we can't do that. So the problem is that you need enough gunpowder to get the parachute out. That there definitely should be a licensed guy there. You know, it's not like party popper kind of gunpowder. It's like a bit more than that. So yeah, so for those smaller rockets, it's like in theory it would be fine, but nevertheless we still can't do it here because like the law says no, you know. But yeah.
Sorry, the law says no, or the law says it requires a license?
Yeah, so the law says you will need some kind of permit and license in Singapore, and in order to get that kind of license, you need to be like some kind of defense contractor or something. You know, a bunch of students can't get it, so we cooperate with people overseas, and then we do everything there. Yeah, yeah. Yeah, so I guess the eventual dream, although of course everything is like so tentative, it might as well not exist. The real dream here is like if Singapore had its own space testing capability, then like maybe we could put our own satellites up, you know. Austin and DSO and such, like they seem to like they support a lot of student satellite projects actually, you know, like NUS and US High, like space faculty, they do satellite projects, and Singaporean students are actually able to participate in these projects, you know. And it would be cool if students could also do something to actually get those satellites into space themselves. So I guess in a way that would be the eventual goal, not just satellites, but really any scientific payload that Singapore might want to do. Yeah, that would be about it. So we're never gonna be, I don't know if, in fact, I'll confidently say that this is not something that intends to become a manned mission kind of, you know, Singapore is like 40 kilometers wide, don't bother, you know, but for something like a sounding rocket that barely reaches like low Earth orbit, which is 3.5 times higher than our current goal, by the way, and is massively difficult. For something like that could be launched, you know, in international waters between like Indonesia or something. You know, one can dream, you know, it's maybe it'll be possible one day, but it really is outside of the scope of like what we're trying to do here. In the end, what we're trying to do is we're trying to reach the Kármán line as like a slightly more manageable goal that other overseas universities have actually accomplished. And we're trying to get Singaporean students into that goal as well, and show you that you can do aerospace too. Yeah.
I'm just curious, right? Like from an organizational standpoint, because it's like a university project, like I'll say there's like a lot of inflows and outflows of people. So how do you manage like a project risk and like organizational risk, like effectively in first part? Second part also is in terms of your PCB fabrication, like what sort of special processes you inform like your fabricator to perform, like given it's I'll say a high velocity and a high temperature environment.
Yeah. Okay, great. So the first question was about organizational longevity. Okay, so at its key, this kind of project, it's nice to have like a faculty or professor who's in charge of that, and he can help with the handover takeover process as new organizational committees move in and out, you know. But beyond that, the rocketry community is actually pretty close-knit. And we have collaborations with all kinds of other teams, you know, in Switzerland, in Australia, in Malaysia, wherever. And in this way, the sharing of knowledge back and forth is generally enough, at least we've observed in other organizations, that it helps to keep the spirit alive, you know. And it seems that there's no shortage of the passion. So as long as there's someone who's willing to teach and someone who's willing to learn, that really is everything you need to keep an organization going. As for special SMT processes, actually, I just select aerospace in the PCB, and like it just adds like 2 more tests, like Kelvin wire test and one other thing, and it forces you to use like a certain kind of fiberglass matrix in the PCB. Other than that, it costs like $5 more, and like the thing's gonna survive. You know, so far we haven't pulled G's enough such that components have literally been falling off the board, and it's quite far out of scope to worry about radiation hardening anything. So we're not quite there yet. So far, regular PCB manufacturing, actually, it does kind of suit what we're doing pretty well.